Today, we're jumping into a real cosmic detective story. The mystery. Well, it's about the suspiciously perfect shape of our universe. We've had a prime suspect for a while now, but honestly, the case is just full of holes. But now, we've got a new clue. One that might just change everything we thought we knew about the very dawn of time.
You know, when we look out at the cosmos on the absolute largest scales, it's incredibly uniform. It's not all lumpy or wildly curved like you might expect. It's almost perfectly flat and smooth in every direction we look. But here's the thing. According to the standard Big Bang theory, it really shouldn't be. So what on earth is going on?
For decades, the go-to explanation for this has been a theory called cosmic inflation. And it's a brilliant idea, it really is. It solves a ton of problems, but, and this is a big but, as we're about to see, this standard answer comes with its own deep, nagging puzzle. A real head-scratcher that makes you think we might be missing a huge piece of the story. So to really get a grip on this puzzle, we first have to understand the problem inflation was even designed to solve in the first place. Why did our universe need this seemingly perfect beginning? Okay, so the core idea of inflation is actually pretty simple, but it's incredibly powerful. The theory goes that in the very first, tiniest fraction of a second after the Big Bang, the universe went through this absolutely mind-boggling growth spurt. It expanded way, way faster than the speed of light, and in doing so, it smoothed out any and all initial wrinkles or curves, kind of like stretching a crumpled up piece of paper until it's perfectly flat. All right, so how is this hyper-fast expansion supposed to have happened? Let's take a quick look at the standard story, the one you'll find in pretty much any physics textbook.
So the standard model pictures this kind of temporary energy field that just filled all of space. They call it the inflaton field. You can think of it like a cosmic rocket booster. The idea is that this field suddenly kicked on, dumped a massive amount of energy into the universe, and powered that incredible expansion. It smoothed everything out, and then, just as suddenly, it was supposed to switch off. And right there, that's where the plot holes in our cosmic detective story really start to show up. This elegant solution, well, it has some deeply unsatisfying problems when you start to look at it a little more closely. Let's break down this cosmic puzzle. Okay, first off, this inflation field, we have never ever observed it or its particle. It's a ghost in the machine, a suspect with no fingerprints. Second, for the theory to actually match what we see, the influence properties have to be tweaked to an absurdly precise degree. It's like needing a dial turned to one very specific number with no explanation for why it's that number. Physicists call this fine-tuning, and they don't like it. And third, and this is maybe the biggest issue, the theory doesn't give us a natural way for inflation to stop. It needs an extra, totally artificial off switch just bolted onto the side.
So here's the crucial point, and the author of this new theory puts it perfectly. These aren't just little details we can sweep under the rug. They're clues, and they're pointing to something big that's missing. What if the answer isn't some new magical field, but a much deeper understanding of the very geometry of the universe itself?
And this brings us to a really radical and honestly fascinating new idea. What if we've been looking at this whole problem backwards? What if the solution comes directly from the fabric of reality itself? So let's ask a provocative question. We usually think of space-time as the fundamental stage, right? The arena where the universe plays out. But what if space-time isn't fundamental at all? What if it's an emergent phenomenon? Meaning, what if it's something that arises from a deeper, simpler set of rules? Kind of like how the complex, interactive world of a video game emerges from the simple ones and zeros of its underlying code.
This is the core idea behind a new model called Conformal Emergent Reality, or CERM for short. It proposes that our universe, with all its time, space, and matter, isn't the base layer of reality. Instead, just like that video game, the world we see and experience emerges from a more fundamental kind of geometric code. And the architect of this emergence, the programmer of the source code, if you will, is, according to the theory, a single dynamic entity called the omega field. If our universe is the video game, the omega field is the game engine. It's the master blueprint for space-time, containing all the fundamental rules for how our universe has to take shape and evolve. Okay, so how does all this talk of geometric source code connect back to our original mystery? This is where the detective story gets really, really interesting. How does this new geometric approach solve the puzzle of inflation so much more elegantly than the standard story? Well, in this new picture, you don't need to invent a special inflation field out of thin air. Instead, the driver for inflation comes naturally from the source code itself, a tiny quantum ripple in that fundamental omega field, which the theory calls the omegon, is all you need. See, it's not an add-on, it's a built-in feature of the system.
So let's compare our two suspects, side by side. In the standard story, the inflaton is this mysterious outsider, brought in just to solve the case. But in CRM, the omegon is an unavoidable consequence of the universe's basic geometry. And here's the real kicker. Standard inflation needs that specially designed, fine-tuned off switch to stop it. CRM's inflation, as we're about to see, stops all by itself.
This, right here, is the most elegant part of this whole new theory. It has a natural, built-in off switch. The end of inflation isn't some awkward afterthought. It's a direct consequence of the process itself. Here's how it works.
Okay, so in the very early universe, space-time was incredibly curved. You can imagine it as being really tightly wound up. This high curvature is what gave the omegon field its power, and that's what drove inflation. But as the universe expanded, that curvature naturally relaxed and decreased. And since the omegon's energy is directly tied to this curvature, its power just automatically faded away as the universe flattened out. Inflation simply gracefully runs out of steam. No off switch needed. It's beautiful.
Now look, this is a fascinating idea, a really cool story. But a good scientific theory can't just be a neat story. To be taken seriously, it has to make concrete, falsifiable predictions, things we can actually go out and look for with our telescopes and our experiments. And this theory does exactly that. It predicts specific fingerprints left over from the dawn of time that we should be able to find. For example, it predicts a very specific kind of twist, or tilt, in the gravitational waves from the Big Bang. It also predicts that we should be able to see these unique concentric ring patterns in the faint afterglow of creation, the cosmic microwave background. Finding these specific signals would be like finding the suspect's DNA at the crime scene. Just incredibly powerful evidence for this new geometric picture of our universe.
And this brings us to the final, really profound question this theory leaves us with. For centuries, we've thought of geometry as just the stage. But what if it's the main actor? What if the geometry of space-time isn't just the backdrop for the play, but the ultimate cosmic architect, shaping everything from the very first moment of creation to the galaxies we see around us today? It's a truly mind-bending thought, and one that future observations hopefully will help us answer.